Good evening, everybody. Welcome to Virtual Night Sky. This is our version of Virtual Night Sky for July the 13th, 2022. This particular program, sometimes I forget to say, is actually presented by the School of Earth and Space Exploration at Arizona State University. We're located in a really wonderful building. It has a funny name. It's called ISTB-4, but it's on the main campus in Tempe, Arizona. And so I know some of you have visited us. Some of you will visit us. We're kind of in that little midsummer thing when we're doing a lot of construction and we're building some new things and changing around some exhibits. But we'll be sure to announce on this show when we're done with all that and we have things for you guys to come see and look at. My name is Rick Alling, and I am a manager of community outreach. And in my realm, the place that I work is in that building, the first two floors of the building. If you were here with us last 2 weeks, right, we visited the Meteorite Center on the second floor, and we got a really, really good chance to go into the Meteorite Vault. We worked with Lawrence Garvey, and he showed us around. That's kind of the place where we work. And we're just very, very pleased to be able to take this and turn it into a virtual program every 2 weeks. We'd love the opportunity to get in front of you and share with you all kinds of different things, different topics. Tonight, the main thing is we're going to talk about the James Webb Space Telescope. And we'll get to that in just a minute, but I'm going to do some introductions and some housekeeping, and then we'll sort of start our program. I introduced myself, but always with us and a colleague of mine. I've worked with her for, oh goodness sake, she'll probably help to remind me, but it's been nearly 13 years. Meg Hufford, she had the week off 2 weeks ago, and but she's back with us tonight. And she's always kind of helping us move things forward and keep us on track as we go forward. I know I always introduce and thank Kim Baptista, deservedly so. She's your webmaster, and she's the one that sets up these webinars, and she gets the communications out, and she's the one that kind of keeps that particular part of the technical part flowing nicely, so the rest of us don't have to worry about that. And thank you, Kim, for all of that. Just after a recent promotion, you have met Alicia Hyatt before, and she's been was made a staff member about maybe 6 months ago, and now we've sort of been able to realize that more fully. And so Alicia will be with us, and she'll be taking more and more responsibility on this program and others going forward. So she's with us tonight. And two amazing students, Alex Blanche and Armand Dalla. They have been with us now for several weeks. One of the reasons they're on board, and you're going to meet all of these people tonight, one of the reasons they're on board is they work in the background and they also field questions. So this is a good chance for me to kind of get you involved and suggest that if you want, and we encourage this, we are a webinar format, so you can't just chat with us. That function doesn't belong in it or doesn't work in here, but you can do a question and answer. And so on the bottom of your screen, little Q&A button, press that, add a comment, add a question as we go, and it is being looked at in the background, and many of those questions are just answered outright, or they can be brought forward to a session. We can do those live on the air. So please take advantage of that. Have anything you want to say or want to do, we'd like to do that. We do closed captioning, and it's kind of up to you whether you want it or not. You have the ability to turn it on or off of your own computer, so you can do that as well. And we always like to suggest to people they just sort of just do the view at full screen and maybe minimize the side stuff, because we've got a lot of really amazing things to show you, and those will look better in a full screen format. So we always encourage that. Tonight we're going to spend a lot of time talking about the James Webb Space Telescope and those images, but later we'll have a little sort of introduction and a sort of some upcoming meteor shower events, because this is that time of year we're looking forward to some. And then it's a full moon today, so Armand is going to come on and kind of give us a little bit about history and lore and full moon and what this one is all about in the middle of the summer. Speaking of middle of summer, I was able to take a little time off and go up north, northern Arizona, and then on up to actually north of Durango. Some of you will probably know there's a beautiful lake and a river up there called Vallecito. So I've been actually out of the office for a while. I came back and we've got a lot of really wonderful things going on. And I also came back to the heat. So I just checked at showtime. I'm looking at my little my watch here. It's 108 degrees outside. This really is the hottest part of the summer. and it is an astronomical phenomenon that makes that happen. But that doesn't mean that we want to see it sort of go away. Let's see if we can make that sun sink down a little bit more in latitude and give us some refreshing fall breezes, and then we'll look forward to the winter. But right now, oh my goodness, this is brutal, and the summer is really hitting us right hard right now. That doesn't stop us from looking up and looking out and seeing some amazing things. So what I wanted to start with tonight is a real quick poll question. As we announced a couple of weeks ago, we anticipated that yesterday, July the 12th, was when NASA and the Space Telescope Institute were going to release the very first images of the James Webb Space Telescope from the James Webb Space Telescope. And so that happened. I'm going to give you some context. We're going to make our way out into the universe, into the realm of where these images come from. And in the meantime, we've got a little poll launched here. So if you would quickly take a moment, let's just see how many of you were able to take advantage of that. You watched the news, you might have watched the broadcast. It was yesterday morning, 7:30 our time, and it was really quite special. It was really wonderful. At the theater, at the Marston Exploration Theater, we had a chance to have some of the staff in, and we had some of the press come by, and we heard some comments from Regents Professor Roger Windhorst. Roger is a professor at the School of Earth and Space Exploration, and he has been involved since the get-go as a science advisor to the Space Telescope team. So designing the instruments, what they're going to see, what they have to, how they have to be designed to see the targets we want to see. All of that science in the background is done by a number of people from around the world. And fortunately for us, Roger Windhorst does that right there. So here we go. About more than half of you were able to watch the unveiling. Less than half of you weren't, but this is, you'll get a chance. And tonight we're going to go there. We're going to go there in a very special way. So let me get started. Shall we do that? I'm going to use sort of a borrow, if you want, a program. Let me just change my screen. I'm going to turn that off. I'm going to borrow from a program. We use it at the Marston Exploration Theater. And that, saying that name just reminded me, I believe, if I have this right, maybe one of my colleagues can correct, but I believe Susie Marston is actually watching tonight. Susie Marston is a friend of ours and was the original philanthropist and donor that kind of got all of us started, our theater, outfitting the theater with this amazing technology. The technology I bring home and kind of showing you tonight actually kind of came from her and her largesse. And so we really want to welcome Susie to the screen tonight. Thank you, or I mean to the program tonight. Thank you very much. I'm going to kind of switch over to that view. And if you've watched this before, you've sort of seen what I can do is I have control over this and flying. I'm actually flying live. So not only am I talking to you on one computer, but I'm actually operating another one in the background. And this gives us enough control to kind of like get in here and see. And what we'd like to do when we're in the theater, I'm going to just kind of like switch to now just to make sure I got the timing right and flip over to our side of the world here. And what I'd like to do is just start with this particular view because this is where we are. And space is away from us, is out in the distance. And so we're going to kind of start a little, really quick little journey, borrowing from some of the things that we do on campus at the Marston Exploration Theater. And we're going to just kind of get way, way out there. So we're in the middle of this little screen someplace. You can see it's dark over in Texas, but it isn't quite dark over here. As far as I'm concerned, it can't be dark soon enough. Let's get that sunset and things starting to cool off. As I back out here a little bit, I'm going to just sort of like just introduce you to some things as we go. There's the moon. It's a full moon tonight. In fact, if I organize it so that the moon is kind of on our side and the Earth is on the other side, you'll see it. It aligns very nicely with the sun right now. So because it is a full moon, there you go. And so let me just keep backing out. I've added the orbits of our planets. They don't really have orbits in space. You can't really see them, but I've, in my particular flight here, I've got them organized. You can see that we have 4 inner rocky planets. The blue one is the Earth. The red one is Mars. And we can kind of move out. I forgot to show you something while we're way back in here. I wanted to sort of tell you a little bit about the James Webb Telescope as opposed to the Hubble Space Telescope. If I get the sun and the moon, the Earth and the moon into view here, the Hubble Space Telescope is very close to the Earth and orbiting right around us. It's only about 340 miles over your head when it goes by. And so it's an Earth orbiting piece of gear. It is a telescope. It's looking out, not in, but it's very close to us. On the other hand, the James Webb Telescope, the new one, the latest, greatest, actually is out beyond the orbit of the moon. So instead of orbiting the Earth, the James Webb Space Telescope is actually orbiting the sun with us, if you can sort of understand that. So we are out, and that means two things to us. One is that it's not serviceable. It's out there in space, way far away from us. It's in what we call a Lagrange point, which has to do with the gravity between the Earth and the sun, and a calculated area where there's a little eddy in that gravity. And but it is actually way away from us, very different in its approach to looking at space because it's not tied to our orbit. It's orbiting the sun in 365 days, just like we are. Let me just kind of keep backing up then. I wanted to stop there. The outer gas giants are out here, and we can talk a lot about the solar system, but we're going to get beyond that very, very quickly. And I'm going to light up just some labels of some nearby stars. As I back away from our solar system, we're going to leave it behind. And we're going to start getting way, way out into space. As I see some familiar star names coming in, I'll slow down a little bit. Yeah, so in your night sky, for example, you can see Sirius and Procyon. The one that says A Cen, that's Alpha Centauri. It's actually, it's in the southern part of our skies, so you won't see that one. You have to travel to Argentina or Australia to see that. You see Fomalhaut, Altair. These are all sort of stars that are familiar to you. When you look up at the night sky, when you see your constellations, these are the names and the stars that are around us and make up a part of our night sky. In the background, you can see sort of starting to come into view is the main dust lanes of the Milky Way Galaxy. So if I get way, way away from our familiar place and out into a more galactic view, you'll start to see a little bit of that distance. And I like to do it this way because we're not changing slides here. We're actually free flying. So our solar system, the familiar stars that we know, are on one of these spiral arms. We're not close to the center of this galaxy. We're about 2/3 of the way out. And this collection of stars, about 200 billion in the night sky, we call the Milky Way Galaxy. That's our home. So we have several homes. The Earth is our home. The Earth and the Moon are our home. The Earth and its planets, our solar system is our home. And then away from that, our local sky, our local stars that we get to look at are our home. But now we're way, way away from all of that. And it would be, our view here is probably from about 100,000 light years away. So I've moved impossibly fast way out here. We used to think that our galaxy was probably the only galaxy in existence, right? We didn't know. We couldn't see distance. We couldn't see very far out into space. But then we started to discover that we are actually surrounded by many, many galaxies. And so I've lit up a little data set here. I'll scale up some of these so they look like galaxies. And you'll start to see that when we are surrounded in space, not by stars, but by islands of stars, galaxies that sort of surround us. This is all part of what we call a local group. So we're moving kind of fast, and I want to recap a little bit, right? We went from the realm of our sun to our neighboring stars. We moved out and saw how those stars might be embedded in a collection of 200 billion stars called our Milky Way Galaxy. And now we're moving out to a surround of galaxies, 150 of them that are dancing around with us in space. Out here, there's one very familiar one that you might know is called the Andromeda Galaxy, and I might be able to maneuver so I can get it kind of close to us. The Andromeda Galaxy is a galaxy very, very much like us. I found the wrong one. Is very, very much like us. It's about 2 million light years away. 2 million light years away. So we went from stars that are very close to us, 4, 5, 6, 2,500 light years away to the farthest stars. And now we're out here in a realm of galaxies that is way, way, way out in space. Let me see, I might be able to add a grid here. Let me see if I can do that. This grid that I've kind of thrown up on the screen here, I'll back out a little bit. It is centered on our galaxy, and you can see that that designation over on the right side of the screen is 50 million light years. So all of those galaxies close to us are in the 2 to 20 million light years away, and in this particular data set there aren't any further, but we have more data sets. If I just sort of like light up more galaxies, this data set here, and this is really beautiful in our theater. So when we're open and you have a chance to come visit us, I want you to come see this. In this particular data set, there are about 750,000 galaxies. So now we've moved from our sun out to our galaxy, our Milky Way. We saw the galaxies that are near us in our own neighborhood, and now we're moving out. This is called the Tully-Fisher All-Sky Survey. And what this shows us is not only essentially galaxies everywhere, but a little bit of sense of structure, the structure of space. We're not going to spend much time with that tonight, but the idea of mapping galaxies at this level also gives us an idea, kind of tells us the story about how these galaxies formed, which ones are attracted to each other, where there's pockets of many, many billions of galaxies really densely packed, and when there's galaxies that are kind of loose and free and kind of running on their own. This next set that I just lit up, all the sort of like green things, you can see the Tully-Fisher one in the middle. I'm going to turn that off because it just sort of seems to interrupt with our scene here. And this is actually what we call 2MASS, 2-micron all-sky survey. Now, I'm going to just pause here for a moment because I want to put the context to what we're seeing here. Our Earth is in the middle of this system. We can't fly here, but we invent devices, we invent telescopes, we invent ways of seeing very, very, very deep into space. And so from our point of view, we can start to map the sky. Each one of the dots on this screen, and there are hundreds of thousands of them, are an actual galaxy in space. The color coding here, you see little groups of red, those are really, really dense areas, concentrations of a lot of galaxies. And this is really sort of part of understanding space and how deep space is. This is how we do it. I'm going to turn on another grid so we can kind of get another sense of scale here. And so remember, we're in the center. And in this case, each one of these boxes represents 1 billion light years. So when I see on the right side of the screen down towards the lower right, it says 5 GLY. That's 5 billion light years from the center of the Earth out to this area. That is essentially, you can kind of look here and you can see that the limit of this particular survey is, I would say is about 1,200, a million 200 1,200 million light years. Sorry, I'm getting my big numbers confused. But there's another one. There's a survey going on, and you can see it's not complete. It's looking out the top of our galaxy and out the bottom of our galaxy, and together it has collected a whole realm of galaxies that sort of stretch out into space. The reason it looks like an hourglass is that it's hard for this technology to see through all the dust and debris in our own galaxy, so we don't bother to do that. We look out the top and the bottom. And this is called the Sloan All-Sky Digital Sky Survey. And you can see sort of in the bottom part of the screen how this sort of works. We organize to sweep through the sky. We collect data about different galaxies. We put the points on a map. And then we can see in 3D scale essentially what this looks like. And you can see that Sloan goes way beyond the previous galaxy surveys. And now we're out to, I'm going to say, about 6 billion, maybe almost 7 billion light years as we're detecting these big galactic structures way out into space. Okay, got one more to show you, and then I think we're going to kind of just move out and show you why this is important. This little sort of like white line that I lit up on the screen right here is actually not a line at all. It is a line of sight, if you want. And these galaxies, this data was collected by the Hubble Space Telescope, right? The one that was replaced by James Webb. And the Hubble Space Telescope was able to take us way, 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 way out into space. You can see this is actually what we call, it's the experiment here is to take the Hubble Space Telescope, the greatest instrument invented up until James Webb, and point it at a tiny, tiny part of space. And we call these ultra deep fields because they're like many, many hours of time goes into looking at one tiny piece of space. And with that, the Hubble Space Telescope can collect data on galaxies. Well, let's look at it for ourselves. Look how far away this is. So now I'm going to actually have to explain a little physics here because it's going to be necessary to do that. You see a grid in the background that suggests that the outer part of the grid is 20 billion light years away. In this particular scene, the galaxies that are making up this Hubble deep field and stretching out into space represent where they are now, not where they were when they started their light journey towards the Earth. So that's kind of important because the next thing I'm going to light up is what we call the cosmic background radiation. That particular field of color out there is actually energy that is caught in microwave, right, by using technology that reads microwave. And it is the remnant energy from what we understand as the Big Bang. That was when the universe started. And the universe has been cooling and expanding ever since, right? It's been as it's been doing its journey out into space. And so what this means is that we are not going to be able to detect anything beyond that field, that sort of color field of cosmic background radiation, because it represents sort of the edge of our universe as it's expanding. Everything we know, everything we see, everything we can detect with whatever telescopes we build has to be within that particular envelope, because that is the background radiation from the beginning of our universe. But you can see, look at this, look at how far the Hubble Space Telescope has been able to take us out on this journey. This is where I need to really stress this comment, is as we look out, we're looking back in time. So the galaxies that we see out at the end of this field, at the very, very end of that little pencil point, at the furthest reaches of what Hubble can see, are about 13.1, 13.2 billion light years away. That light started 13 billion years ago heading towards us, long before there was a sun, long before we had a solar system, long before we had an Earth. That light started its journey. It finally caught up to us once we were able to get the Hubble telescope up into space and start to see and collect this information. Here's the cool part. The James Webb telescope is working. It has taken us to a new level, and it will extend our view out beyond what the Hubble view was and out toward the cosmic background radiation. So if you see sort of the end of my little line of galaxies that is the collection of data from Hubble and out to the edge of our known universe, that is the area, one of the areas where the James Webb telescope is going to take us. some of the images that were collected and distributed yesterday sort of reinforce this idea and show this field. So what I'm going to do is I'm going to leave us here. We've taken a long journey. We've left our Earth, our solar system, to a galactic view, out to a collection of galaxies, out to a field of galaxies, which is sort of the most distance we can see with our current technology. And now we're going to kind of switch over. I'm going to invite Alex to come to the screen, and he's got some images and some comparisons, and Alex and I are going to kind of work together and show you about the Hubble Deep Field and what it means. I'm sorry, the James Webb Telescope and what it means.
Well, we can talk about both. Thank you.
Yeah, I guess we are going to talk about both a little bit.
We kind of already have. I mean, you can't talk about James Webb without Hubble, and now you can't talk about Hubble without James Webb. They're very important siblings.
Look at our backgrounds. Look at this. We have actually sort of like celebrating tonight. Some of these backgrounds are actually from the collection of images that were released yesterday. So let's see what that looks like.
Yeah, so I guess we'll just hop in and start talking about these images.
Please do.
I think that'd be the way to do it. So let me just make sure that everything's set up for screen share. So for those of you who I guess don't know, 5 images were released so far, James Webb. 1 was released on Monday, and then 4 more released on Tuesday morning. And that was kind of the big press conference that we were polling everyone about. So this first one is a deep field image of James Webb. This is actually of a galaxy cluster called SMACS 0723. So this galaxy cluster, you can kind of see that it's these 2 bright kind of spots in the middle. This is kind of a galaxy cluster. A lot of galaxies really close together here. And the reason we want to look at these galaxy clusters is because galaxy clusters have so much gravitational waves and kind of gravitational effect around them that they can begin to lens space-time. And this is what you see, these little streaks are galaxies being lensed and magnified by the gravitational waves around these really dense gravity clusters. And these are important because they take galaxies that are really distant, really dim, that we wouldn't be able to see, and it makes them visible. And so when you're using a great telescope like James Webb, and we've also done this with Hubble, is you can actually see very distant objects much further than you'd be able to see normally. So this deep field was about 11 days exposure. The Hubble Ultra Deep Field was actually about the same time, but whereas James Webb just did 11 days straight, and that was that, Hubble had to do it over 3 months because it was orbiting the Earth. So this is kind of the first deep field image of James Webb. You can see these galaxies stretched. You have galaxies that are, I think, 13.1 billion light years away. So these are getting really close to the furthest we've ever seen with the telescopes we had previously. And this is just kind of the warm up. James Webb has capabilities to observe for even longer and see more distant galaxies. So this was just kind of the, can we do deep fields, and just kind of set the benchmark. So this is very interesting. And as we'll talk about a little bit more, but you can actually see the comparison between, or actually I can probably do it now. I'll compare the Hubble and other deep field image compared to what Hubble did of this galaxy cluster. You can see here, so here's a James Webb. Oh, it's not gonna let me work real quick. Let me refresh it real quick.
I'm going to just kind of amplify something you said about lensing. And so just to sort of clarify, is what's happening is those little arcs that you see on the screen are actually not the positions of those galaxies. The light is being bent around the mass in the center. And so there's a big mass out there. Galaxies that are behind that mass normally wouldn't be able to be seen because they're behind all those other things. But this mass is so strong that it's taking the light of those galaxies and bending it, kind of curving it through space. And so when we see all those little arcs, you're seeing just sort of a collection of galaxies that are, you know, as Alex says, it's way, way in the distance, way beyond the field of view in front. You can also see like the little arc that is to the left of center there. It actually is, you can see there's 2 little streaks there. Those are the same galaxy. So this is kind of a little trick in space. They're both essentially reflections of the same galaxy that is way back in the background. What this does for us, though, is it allows us to do spectra from those galaxies, and we can tell a lot about their development and all of that stuff, even though they are way out there in the distance, and even though they're way beyond this normal field of view that we might have. And so gravity lensing is a really important tool for science to do the research. Okay, so I think you've got it up here. So
we got the comparison tool. Okay, good. So yeah, so this is the James Webb image, and now we can start to pull this over. It's not going to work now even. Oh my gosh, the technology's just.
It actually went up and then it sort of like stopped.
It
The other
stopped.
thing, if you try to do it one more time, we also need to talk a little bit about color here. And you can just see readily, just looking at this image, that there you go, that there's a big variety of color. There's things all the way from red reds to light lights and blue blues and all that stuff. The red stuff is important because aside from being a bigger telescope and being positioned in a different part of space away from the Earth and the Moon, so it has a better sort of like outlook of the entire sky, it also is tuned farther over towards what's the infrared part of our spectrum. Hubble shows us visible light, the stuff you can see with your eyes, the rainbow, the red, blue, green, orange, yellow, that kind of part of it. Webb actually is sort of more pushed off of the side of the spectrum that we can see into the infrared. And so watch what happens here as Alex does some little comparisons as he moves by. You know what it is, Alex? I don't think you can move that far away from it. Go ahead and leave the image kind of in the screen, or the marker in the screen, and that it'll work.
And you know, it's just the perfect timing, because right before it was working perfectly before.
I know it is. So color is important. The other part of the color thing that is really important for James Webb is that our universe is expanding. Remember when I was showing you the view of our galaxies and that background radiation, and it sort of looked like a sort of a ball, if you want? That whole thing is growing. We are still expanding. And that means that the outer part of our universe, this galaxy, where these galaxies are, they're moving faster away from us than the galaxies that are close to us. And as things move away from us, they also shift in spectrum. So if they're not moving at all, they might be sort of a yellow, red, orange color. As they're moving, the faster they go, the more they move over towards the red part of the spectrum. And there are galaxies that just move out beyond our ability to detect them in visible light because they have completely shifted over into the red side. Okay.
So now you can see really well.
I'm going to stop talking so you can sort of like show this. So,
yeah. And another important thing about Hubble and James Webb in terms of their wavelengths is Hubble did have infrared capabilities. It could see into the near infrared, but the thing is, infrared's a longer wavelength than visible light. So the thing is, for a smaller telescope like Hubble, the resolution is very decreased in the infrared wavelength. Well, James Webb is much bigger. It's specifically designed to see infrared. So actually, James Webb has the same resolution that Hubble did in the optical in the infrared, which is very important. And it's beyond that in some of the near infrared. So as you can see, a lot of these objects become much, much clearer. And actually, you'll notice, like, especially like these galaxies right here, they completely disappear when looked at through Hubble because they're completely invisible in visible wavelengths. So you have to have those high infrared capabilities on James Webb to see them.
Just to make it clear, so the left side of your screen is the Hubble Space Telescope view.
Correct. Yeah.
The right side of your screen is the James Webb Telescope view, and we're just basically running a little sort of like a comparator line across, so you can, as he moves back and forth, you can see there's the Hubble, there's James Webb, and you can see a tremendous amount of difference. It's not only the resolution, how crystal clear some of these things appear, but also just the amount of galaxies, the amount of light, the amount of spectra, especially the important light that we need to find that is that of these infrared colors and things. It's just absolutely amazing.
I mean, the thing that, look, even this galaxy in James Webb, you can see its galaxy, and here it's just a blur in a Hubble. So it's really incredible, just especially here. But this isn't just the only image that we've taken on James Webb. I think we want to show the others, don't we?
Yeah, go ahead. Okay, go ahead. We're going to get stuck. I knew we would kind of be able to talk about this forever.
We can talk about this stuff forever, but we want to make sure that we get to all of them. So
what everybody is saying is that we knew that we were going to be an improvement. We knew this was going to be better. We could scientifically say we're going to be able to do this and all this stuff. But all of the researchers that we know and what they've sort of announced on that thing is it's just dazzling. It's almost overwhelming. And the amount of sort of new information that we're going to be able to get is awesome. Go ahead.
It's really incredible. Here's another one, Stephan's Quintet. I think we kind of touched on this. This is another galaxy cluster. These galaxies are all close together. This one's actually, it looks close to the others, but it's actually just closer to us. It's pretty separate. But these are actually two colliding galaxies. But as you can see, so this is in the near infrared. So this is kind of similar to what Hubble might see. But as we go into the further infrared of James Webb, we start to see these lines of hot gas This is basically hot gas like hydrogen and helium, and it's being flung out of these colliding galaxies, being heated up and flung out. And that's very neat to see that, because you can actually see that mechanism of the galaxies.
We're actually watching a collision of galaxies happen right in front of us. I mean, they're actually just basically colliding with each other as we speak. I think that's amazing.
It's really incredible. And the other thing is, the thing I really like about this image is, so this isn't the full resolution. I'll skip over to the I have a full resolution of this image pulled up, which is really incredible. If I can get to, yeah, here we go. And then you zoom in and you zoom in and you zoom in, and just look at how many actual like stars you can make out in these galaxies. All these little dots of light that were blurs in Hubble, you can now individually pick out and see. And that's a testament to the detail of James Webb, is how much of this, how individual stars in these galaxies that we can actually see and pinpoint, which is really, really incredible. So just the detail on these images is phenomenal. And this is a huge image. This is, I believe when we were talking about, these images are like 10 gigabytes each, the raw scientific data. And once we get really into the pipeline of James Webb sending off images, we're getting terabytes a day that we have to find a place to store and then analyze. So it's going to be busy, but just the detail on this is just phenomenal. In addition to the fact that, we're seeing the universe in a whole new wavelength and a whole new detail. So it really is incredible. And then the other thing is actually, so we looked at it in the near infrared, we looked at the composite. This is actually the near infrared and the far infrared combined, the two instruments on James Webb. But then we can look purely at the far infrared, and we can see, one, it looks very, very different. The color calibration is different on this image, but up here, this galaxy is so much brighter. And it's because there's a supermassive black hole that's very active. It's eating a bunch of stuff around it, and it's shining brightly, and it's heating up all this gas around it. And that's something that we can't see with Hubble. We can only see it with James Webb. And so you can understand more about what's going on in these galaxies by looking at it. And you can see this black hole just having its nice little feast while these two other galaxies below it collide. So just really neat.
Absolutely remarkable.
And so actually, let me pull up the comparison from this for Hubble, because we also have all these images. We have a comparison for Hubble, and actually maybe I can share that link as well at some point for.
You would be able to, because everybody. Well, that's actually a good point. So just to give you a little context, all of this information was actually collected by the telescope within the last week or two. So this isn't like it's been out there for 100 days. It hasn't been like this is actually last week's stuff, and we're seeing it now on our screens. And this is just the beginning. This is just sort of when they sort of have the technology, have the telescope turned on, have it making, seeing targets, and they're starting to release the images. As Alex said, there's gigabytes of information coming down every single day. So we're going to see more and more and more of this. And as researchers get to analyze it and to kind of extract out the data that they need from these images, it's going to tell a billion stories without question.
This is just the beginning. And here's that same Stephan's quintet in Hubble. By no means, it is still a very beautiful, detailed image of these galaxies. But especially once you start to zoom in and you start to switch over, you just see so much more. And you just see so much more of these galaxies and the detail in them. And I mean, you can see these little dots start to become fully formed spirals of other galaxies behind it. And that's something that's really incredible and something we don't get to see on Hubble. So again, the detail in these images, let alone the infrared capabilities, is really incredible.
I feel badly like we're dissing Hubble. It's an amazing telescope, right? And it actually got us to this point, and that's the other part of it. Is we have to start with technology, we deploy it, we see what the potential is, we develop newer and better technologies.
Exactly, and we would have never even thought about developing James Webb without the capabilities we found from Hubble. Without Hubble doing that first deep look into the universe and really understanding, we wouldn't have gotten to James Webb. So, and Hubble's still a very premier UV and visible image telescope. James Webb doesn't have UV. If you want to look at something in the UV, you have to go to Hubble, because Hubble's still the number one. So, I'd say always Hubble's my favorite.
I believe, Alex, I heard from Dr. Windhorst that your field is actually more towards the UV. Isn't that where you sort of
So he's trying to get me. He's like, well, you should start doing infrared work, because that's where James Webb is. But if you're going to stick with UV, then you're fine with Hubble. Yeah, because James Webb, we can't do anything in the UV. James Webb's on the other side of the road in comparison. So UV information is still on Hubble. So yeah. This is less a physical image and more just a graphical representation of the capabilities. There's a lot of science and probably someone that could really be excited about, but this is a spectra, a measurement of the levels of light coming off of an exoplanet around a star. This is WASP 96b. The big takeaway is, one, this is an incredibly accurate and detailed spectra of a planet. We didn't get these detailed spectra on any other telescope. So the detail, these peaks and curves are so much more detailed than they would be anywhere else. And so that allows us to measure lines of like water. This isn't liquid water, by the way. This is all water vapor. This planet's very hot, but we can actually now have a very detailed spectra, not just for exoplanets, but for galaxies, black holes, everything, to better measure and understand compositions and what the universe is like. So when we look at these deep fields, we might be able to pull a spectra off these galaxies and start to understand like if these galaxies are some of the first that ever formed before these heavy metals started being formed by stars. So James Webb, the detail isn't just in the image and being able to see those nice tiny little pixels, but it's also in the scientific data that we can pull from those as well.
I should make, and let me do a little comparison or clarification here. I took everybody on a journey way out to the very edges of what we've been able to see, but by no means is James Webb only trained on the far, far distant. These are actually, this image and this planet is in the realm of our stars, the place where we are. So these are these are our stars that are very close to us, planets orbiting around those stars that are very close to us. And so the versatility of an instrument that can see, it will be even at times trained on our own solar system when it can. It has relationship with the sun and all that. But that's kind of, it's an interesting point. The other thing here is that it's not looking at the planet itself, it's actually looking at the light passing through the planet's atmosphere. And so this is what we're measuring here. And what this shows us very clearly is that there is a lot of water, H2O, in the atmosphere of this particular planet. The planet itself is Jupiter sized, and it's moving very, very fast around a star that is much, much, much smaller than the sun. So it's not like us yet, but it is characterization of an atmosphere that we couldn't do before. That's a very, very important part.
Yeah. So, there's so much capability, and, even exoplanets aren't the closest thing James Webb observing. It's going to be in the solar system pretty soon. They're targets of our own planets that we want to look at. And so, even though we've seen these planets in a lot of very high detailed observation, they're not far away by any means. Just using the capabilities of this very technically, logically advanced instrument is always of some benefit. You can always learn something more. We have some more. We're back to kind of classic images. This is the Southern Ring Nebula. There's just a few things. There's this little band, this kind of line right here. That's actually a galaxy, another galaxy, but it's edge on. We're viewing it from the side. So instead of a circular spiral, we're just seeing that edge. But the other thing that's really important, so this is actually a planetary nebula. This is a star that doesn't go supernova, but sheds out all its layers and kind of leaves them all behind. So this is what we're seeing. This is actually what our sun's going to do. Our sun's going to form a planetary nebula and kind of just shed its layers slowly over time. But the thing is actually, so here we can see this really bright star. That isn't the star that this planetary nebula is from. This is actually a paired star near it. But if you look in this image, this little red dot at the center, that's the white dwarf that this planetary nebula comes from. And this is in the far infrared. So this is the only way we could see this white dwarf, because otherwise it's much too dim next to its little partner next to it. So we're actually able to see that in the infrared, that white dwarf, and then more of its layers. But just looking at the details in these clouds is just so incredible. So we can understand this planetary nebula, and we can actually see the source, a little white dwarf, whereas in the visible, we wouldn't be able to see it. It'd be much too dim compared to everything around it. So this is another just kind of exciting image. And then I think just for the sake of time, we're going to go to the next one. The cosmic cliffs and the Karina Nebula. I mean, this is my phone background now. This is just incredible. Very high star forming region. The important thing though is that something before we couldn't see with Hubble, visible light, dust does a great job of blocking it out. So stars in these very thick, dense clouds of stellar dust, we can't see them, but infrared light can peer right through it, and we can basically see all these stars beginning to form. And actually you can see all these kind of shapes and figures are actually these bright, really these more fully formed stars blowing away all this gas with their solar radiation, solar winds. And so, but it's really neat. We can start to peer into these clouds and see how these star forming regions are working. And so I will show the comparison of Hubble, but Rick, if you have anything to say, while I
No,
do
no,
do that.
this is the Karina Nebula or Eagle Nebula. It's very famous, and this is only a small section of it. The entire nebula is just absolutely gigantic, and so there have you have seen it. It's sometimes it's called pillars of creation, and so but these gas clouds we believe are sort of just is this the soup that stars are formed out of, and the soup that sort of like makes all the elements of the universe possible. And so this is collected into stars, mushed and fused, and then re-exploded back out into space. And that's essentially what we're made out of, if you want to think of it that way. So excellent, excellent.
And then here's that comparison to Hubble. So there's the Hubble image and what it captured, but you can see just as we start moving over, you can see just so many stars, and the detail is just, I mean, it's truly astounding. It almost looks like something that would be made on a computer, a virtual image, but this is an actual telescope data. And so it really is incredible. Just the detail in both scientifically and just visually is something that's never been seen before, and we're really lucky to have. So yeah, that's just, it's really neat. And I think this is just, like I said, this is just the first 5 images. There are going to be so many more, and there's going to be so much important science to be done, but there's going to be so many pretty images like we've had with Hubble, and they're just going to keep coming. And so this is just the start. This is just us testing the waters kind of with what James Webb can do. There's so much more to be able to be done and innovate over the telescope's hopefully very long lifetime. So I think I can speak for all of us when we're all excited.
Alex, I can tell you're excited about it.
I mean, I'm just champing at the bit almost. I mean, just getting to see these first images, like when they did the calibration images, that's astounding in and of itself. But now we have like full images, and like you said, we knew what it was capable of. We knew it was going to be better, but just, I mean, seeing it really puts into perspective just how much better it is, and it's still unbelievable. So yeah, it's very exciting. And
we should say about Webb on the web, right? So there's already websites that are just, the NASA one, the Space Telescope Instrument one, and this you can just follow them. I would imagine starting about now, you can go on about every day, and you'll see some new stuff and some new news and some new science that are coming out of here. So this will be great. Very, very cool. Well, thank you, Alex.
Thank you, Rick.
We're going to take just a little bit of a break. I wanted to ask the team, Armand and Alicia, if there's any questions that they want to bring forward at this particular phase. And I keep forgetting to remind people that you can ask questions as we go along. So let's see what we got.
Thank you, Rick. I'm going to go ahead and launch our current events for this week. Some very exciting stuff happening or happened. So going forward, let's see, we have meteor showers coming up, or a meteor shower, starting tomorrow, June 14th, and it goes all the way through September 1st, but the peak of this meteor shower is really going to be August 11th through the 12th. So if you happen to be somewhere where there's a lot less light pollution and you're able to go and see these meteor showers, it might be a nice experience. However, unfortunately, this year it will be a full moon, so that might put a little damper on that viewing party, but still worth the try. If you remember, 2 weeks ago, we met with Dr. Garvey in the Center for Meteorite Studies, or I'm sorry, in the Busick vault, or the Busick Center for Meteorite Studies. We went into the meteorite vault, and Dr. Garvey mentioned that a lot of people believe that the best time to go and look for meteorites is right after a meteor shower. And we now know through meeting with Dr. Garvey that that is not true. So it would be great to go look at them in the night sky, but not necessarily on the ground. And then future meteor showers to consider. Of course, we have the Perseids in August, but in October, we have the Orionids about mid-month, and then November, again, about mid-month, we have the Leonids, and December, the Geminids. So keep an eye out for all of that, and I'm going to turn it to Armand to close out our current events.
Thank you, Alicia. Let me get my screen shared, and let's talk about the moon. So even though we may not be able to see the meteor showers because of the full moon, the full moon itself is actually a significant one. The full moon is later tonight on Wednesday, July the 13th, and it's actually a super moon as well. So what differentiates a full moon from a supermoon? Well, a supermoon is a full moon that is around or at its closest point to the Earth, which is called the perigee, as compared to the apogee, which is when the moon is furthest away from the Earth. And the difference in this isn't that much when we look at it through the sky. It's about 14, the full moon at perigee is about 14% bigger than it is at apogee, which is slightly visible to us, just enough for us to see a visible change in the night sky. But it is a supermoon tonight, and it's actually the biggest supermoon of the year. It's the point where the moon is closest to the Earth. But tonight's full moon is also called the buck moon. Full moons around the world have lots of different names, and they're each have different meanings based on the culture that comes up with the name. So the buck moon is called that because around this time of the year is when bucks or deer start growing back their antlers. But it also, the full moon of July also has different names from different cultures around the world and around the US specifically. So the Tlingit people of the Pacific Northwest call it the salmon moon, and that's because fish return to the area for spawning around this time of the year. And the Abenaki people of the Northeast of the US call it the thunder moon because of the stormy weather and summer monsoons at this time of the year. But yeah, so tonight's full moon is a supermoon. It's the buck moon, the salmon moon, the thunder moon. And I just want to reinforce that the moon itself has so much culture and history and lots of meaning to lots of different people. So when you're going out, even though you may think you're just looking at the moon, there's lots of meaning and history behind that.
Thank you, Armand. Thank you. Great. And we also, I'll remind people, one of the reasons for doing this program and being virtual night sky is to give everybody something to look at. So if you've watched before, we usually send you out to kind of go see something. Tonight, that's it. It will be unmistakable. You'll walk out of the house after the program. It's going to start getting cool. The sun has now gone down, and just take a look. Big, huge, bright full moon, and it should be just a little bit above the eastern horizon as we're finishing our program. So you got something to look at. You can't look at James Webb Space Telescope images from your backyard. You need a James Webb Space Telescope to do that, but that doesn't mean we can't be in our backyard and moving around and moving about at the same time and looking at and taking in the night sky. When I was on my trip last week, I actually did take a look. I got up before dawn. I got up a little bit about 4 in the morning. One of the places we stayed had a little deck on top. Right? It was just perfect for star observing. And I was able to see that whole line of planets that we've been inviting you to go out and see. So there we were, very, very, very bright Venus above the horizon, and then Mars and Jupiter and Saturn and everything just in a big, huge line. As we go forward into the later part of the year, not only do you have some really cool meteor showers, right? This is that part of the season. We'll start to see those come in. But also, we're going to sort of point out in this program when some of those morning planets are going to start to become nighttime planets. What they're doing is they're kind of migrating across the sky as we go around the sun. They're sort of migrating in the other direction. And so very soon Mars or Saturn will be appearing in our night sky after sunset, and then followed by Jupiter and followed by the others. So we'll have you do that. We'll stop getting you up early in the morning and getting out in the sky. And we'll start celebrating that from our own evening sky as well. I'm going to just kind of talk a little bit about some upcoming things, and especially our event coming up in 2 weeks. We are going to go on the road, And so 2 weeks from now at our program, I'm going to I can't remember the date exactly. I guess it's going to be July the 27th. We're going to actually broadcast from Lowell Observatory, the historic Lowell Observatory in Flagstaff, Arizona. And because we've been putting together that program and talking to people and making a list of all the things we want to discuss, we've decided to sort of make that a super VNS, right? It's going to be an hour and a half or 90-minute program rather than just an hour, because we just all agreed today that there's no way we're going to be able to fit everything into one particular hour. So we're going to do that. And the subject is going to be a couple of things. First of all, we're going to learn a little bit more about the Lowell Observatory and its history and how it's the science it's delivered over time. Right? Remember, there was a time when telescopes didn't fly in the sky and weren't deployed way out into space. The telescopes were basically set up in places like Flagstaff, and what that brought to us, and like going backward and looking at some of the precursors to some of the new technology we have today. We're also going to talk just a little bit about space tourism in Arizona, and we'll have guests to share some of this stuff, is where you can go and where you can see things and where you can sort of like find some of the latest, greatest things in Arizona. Arizona is truly an astronomy state. So we're going to kind of celebrating travel, getting out and finding some of these things. And so that's really our goal, is to do that. Not long after that, we will be starting school again. We'll be kind of like going into the fall season. We're putting together a lineup of every other week, every other Wednesday programs. It'll kind of just take us into the future. And so we've got a lot to work with. Every time we do something, it's a little bit new. And we like that we've got an audience that has been joining us now, a loyal audience and new people coming along. And so please come back and see us every 2 weeks. We'll be here, and we'll keep doing this. I'm going to just give one last shout out just to see if there's any questions that have come up over the course of the evening that deserve an answer, need an answer publicly from our team here. And if not, I'll just sort of like put that out one more time. I'm going to ask Kim if we've sort of covered everything we need to cover tonight, and we might close a little bit early.
I do believe we will. I will send out the link by the end of the week for everybody to register. But yeah, I think we're good, and stay tuned for more exciting things from Webb that we'll share with you.
Real quickly, I just want to jump in because I think we want to share just a couple website links for people to find future images for James Webb.
Just remembering that at the same time you chimed in. So
just to touch on some, we got some great websites, just a few. The first one is, I'm getting a SCI. This is the Space Telescope Science Institute. This is just the main operating foundation for James Webb. This is where a lot of their data will come through. You can see kind of the first images. Great. You can also get a lot of other information about space telescopes out here. You also have webbtelescope.org, another great resource for all of Webb's first images and all the data that's coming through it. And then also there's web.nasa.gov. So you have the Space Telescope Science Institute, you have Webb Telescope, and then you have web.nasa. And all of these are sites where you can find more information about James Webb, including recent data, but the entire mission timeline as well. So if you're looking for more information and wanting to keep updated, that's where you can do it. So keep that in mind as we move forward and upward in terms of James Webb observations and all the science that's coming from it.
Good. And I see on the question and answer, some people are thanking us for posting those little sort of slidey comparison things. I should actually note that we actually do those with lunar too. So next time we do a moon program, I'm just going to register that in the background, but we also do before and after shots of cratering on the moon, because one of the things we keep track of is new craters. And so we can do that and lay image on top of image, and you can sweep back and forth and you can see changes on the moon when those cratering happens. So it's a really fun tool. It's fun to use. I'm glad you've sort of found that. So good. Well, everybody, I'm going to just kind of wrap it up. I'm going to invite you to come back and join us in a couple of weeks. We'll be at cool Flagstaff. Hopefully we'll be sort of outdoors. That's our plan. And out on a new amazing observatory deck that Lowell Observatory has for visitors. And we'll see you then. So in the meantime, keep looking for things, keep looking up every night, and we'll be back with you in 2 weeks. Thank you, everybody.